Yep. Okay. All right. Thanks, Chinmay, for the great introduction. So I was thinking what I could present for this talk, and I thought it's appropriate that we present our recent work, which just got published. This is joint work with Chinmay, Somik, and Aditya, and my student Anjana. So basically, this is bringing NURBS, which is a common tool in CAD, into machine learning frameworks. So before I start, just wanted to give a brief introduction. So when you think about CAD systems or computer-aided design systems, traditionally these are objects are represented in the machine learning community or most deep learning community using voxels. So voxels are basically dividing the space into smaller cubes, and then that way you can represent whether that cube is occupied or not. However, if you actually look into the CAD community or the modeling community, triangular tessellation is much more common. But what is really most commonly used is this non-uniform rational B-splines, which have been really the framework behind CAD systems. So today I'll focus mainly on NURBS and see how we can essentially use NURBS for machine learning applications. So a bit of background for CAD systems. CAD systems usually represent models using what is called as boundary representations. So essentially, the surface of the CAD model is represented using its surfaces, and these surfaces could be triangle meshes or splines, as I talked previously. And then NURBS is sort of the overarching set of splines that essentially is the most general representation that you can have. And if you want to go a little bit more detail into NURBS, essentially NURBS are piecewise polynomial tensor product surfaces, and they are essentially represented by this set of control points. So as you can see in the video there, as you change the control points, you can see that only a small subset of the surface is being affected. And this is what is called as the local support property of NURBS. And NURBS also have another set of parameterization parameters. These are called as knot vectors, and they represent how the surface is represented in the parametric space. So going a bit into the details. So essentially what we want with NURBS is use this newly developed concept of differential programming, which is basically coming up with an end-to-end program that can either go in the forward direction using forward evaluation, or we can back propagate the losses by computing the gradients of the output with respect to the inputs. And the idea is then we can use gradient-based optimization techniques or even the back propagation algorithm to train neural networks. So if we can do that, essentially, we can essentially have NURBS as part of the machine learning framework itself. So essentially, what we are trying to see here is what we call as a NURBS layer, which essentially takes in the NURBS inputs, which are the control points and the knot vectors, and the output is going to be the NURBS surface itself. But then we can then differentiate the surface with respect to these input parameters. So if you go a little bit more detail, like I said, the NURBS itself is represented with a set of control points, and they're also rational surfaces. They also have a set of weights associated with NURBS, and like I said, you also have a knot vector associated with the u direction and v direction. So what we essentially want is this is what is commonly done, where you have a forward evaluation, where you evaluate each point on the surface of the NURBS surface based on these inputs. But then now what we want to do is compare this with, say, a point cloud or any other points that we want to fit the surface over. And this essentially creates a loss. But then what happens is that we need to take this loss and back propagate it to the control points and the not vector. So essentially, this is what we call as the backward evaluation. And this requires this gradient of the surface with respect to the input parameter psi, if the surface itself is a function of psi. And we sort of include this, both the forward and the backward evaluation, into a module, and that's what we call as the NURBS module, which I will go a little bit more detail. So let me get into the nitty-gritties of it a little bit. So let's look at the formulation itself. So if I want to look at the NURBS as the definition, essentially NURBS are mapping from a parametric space to the model space. And without loss of generality, the parametric space is a unit square. And then any point in the parametric space is defined by this U0 V0, gets mapped to S of U0 V0 using the NURBS equations shown here. So the NURBS equations themselves are basically controlled by the set of control points, which are in turn weighted by these basis functions. And these basis functions are piecewise polynomial functions, where P is the degree of the polynomial, and they are recursively defined using this equation, where the pth degree polynomial is defined as a function of P minus 1th degree polynomial, and the multiplied by with a linear parameter function of U. So and the UIs that you see here, these are what are called as the not vectors, and these are nothing but the parametric locations of the control points themselves. And you can essentially recursively define this until you go to the 0th degree basis function, which is essentially a step function. So a typical forward evaluation looks like this. So you first compute the non-zero U basis functions. And I mentioned that the polynomials have what we call as local support. So only a small region have non-zero basis function values. So you essentially compute the U non-zero basis functions, the V non-zero basis functions, and then you compute the product of the two. With the control mesh, and essentially that's how you get the surface itself of the NURBS. So this is the mathematical formulation of the forward evaluation. So you can split the surface definition into the non-rational part and the weights. So basically this W is what makes it rational. And then these are the recursive definition of the basis function itself. Now we want the back derivation or the derivatives with respect to the input parameters. So I mentioned before, you have 4 input parameters. So you have the control points, the weights, and then the U0 vector and the V0 vector. So essentially we can define the derivatives with respect to the control points and define the derivatives with respect to the weights here. Similarly, we also have defined derivatives with respect to the not vector. I have not put here due to lack of time, but you can take a look at our paper. But what we essentially do is, once we have these derivatives, we can construct this block sparse Jacobian for the backward evaluation. So this Bij corresponds to one single evaluated point on the surface. But then if you have a m by n grid of evaluated points, you can essentially construct this huge Jacobian, which can then be pseudo-inverted to get the perform the backward evaluation. So that's all a lot of math, but intuitively what it means is this. So the forward evaluation, if you change the control point, you see that the small portion of the surface is being changed. What the backward evaluation does is the opposite. So if I change a small portion of the surface, how the control points themselves will move. So as you see in the video on the left, you see that as the surface point is moved, you see a set of control points are being controlled by this small point on the surface. So this, we can essentially mathematically formulate it and create this NURBS layer, which we can then use it for gradient-based optimization. So the simplest gradient-based optimization that we can do is do it for curve fitting. So here is an example of increasing the number of control points to perform curve fitting. The same thing we can do for 3D fitting. So these are using different set of control points for 3D fitting, or fitting to a set of control points. So you can sort of see the gradient-based optimization happening as the video is progressing, and it sort of fits the set of control points at the end. We can go one step further and compute the perform surface fitting. So this is example of fitting a surface to the model, or we can do more complicated CAD operations like surface offsetting. So here the red point cloud that you see is an offset point cloud, and then use the NURBS layer to fit an offset surface. Going more interestingly, we can also reparameterize the surface itself. So here is an example where the surface is being reparameterized, and you can see that this was the initial uniform parametric space, or the knot vector, but then this is the reparameterized knot vector. As you can see, the spacing has changed, and as a result, you get lower error in these regions because of the reparameterization. So now that we have a differentiable NURBS module, I wanted to show two applications where we use this. So the first one is surface reconstruction from point cloud. So we took this data set from a prior publication called ParseNet. What they did was they did supervised fitting, where they took a point cloud of 2000 points, and then they essentially predicted the control points and weights in a supervised manner. But what we wanted to do was do it in an unsupervised manner. So essentially what we do was we added our differentiable NURBS layer on top of the spline net. And this essentially predicted a B-spline surface, which we can then compare it with the initial point cloud and train this whole network in an end-to-end manner. So that way, we don't need any supervision of the control points. And by doing that, we can essentially fit these surfaces. So these are some anecdotal examples of the fitted surfaces. And not only that, since it's an unsupervised method, we can essentially change the number of control points that we use to fit. So we find that with these simple surfaces that were in the data set, using a fewer number of control points essentially gave us better results. And not only that, numerically also, we got almost 2 orders of magnitude better fit compared to the supervised spline net approach. Going further, what else can we do with such a NURBS module? We can integrate it with a new analysis technique called isogeometric analysis, which essentially uses these NURBS basis functions to perform finite element analysis. So the idea is then you can have smooth solution fields which match the geometry that we are solving it. And essentially, we integrated this with a valve design approach, where we treat we model the valve using NURBS surfaces. But then what we can do is we can represent the the control points as essentially the XYZ coordinates as the red, green, and blue channels of a texture representation. And what we essentially ended up doing was developing this autoencoder architecture, which makes use of this approach called NURBS-aware convolution to essentially predict what the deformed shape of a valve geometry is going to be, given the reference configuration, which is the undeformed configuration. And by doing that, we can essentially predict much faster than doing a full finite element analysis, the deformed configuration for the valve. So, hopefully this gives you an idea for sort of the use for such a NURBS module. So essentially, we developed this differentiable framework for NURBS. And please take a look at our paper, which just got published in Computer-Aided Design. And we have also made our code public. So please feel free to download and play with it. And sort of the future work for this is, one thing I didn't talk about is CAD systems also have what are called as trim NURBS surfaces. So these are surfaces with holes, and how to deal with them would probably be our next step in this process. So with that, I would like to acknowledge my lab, also my students, and my funding sources, and I would be happy to take any questions.